There's a single core concept which threads through all of mathematics, and if you don't understand this concept, then you'll be stumped by many different questions at the university level. In fact, there's actually a question from the University of Melbourne in the linear algebra course where I was a tutor for many years that I saw student after student fail. Not that they got it wrong, but they had no idea how to attack the question because they didn't understand this singular concept. And this concept is, very deep in all of mathematics. And the concept is about inverses. So first I'll talk about the concept, and then I'll show you the question that almost all of the hundreds, well over 100 linear algebra students I personally tutored, as a tutor there, they all failed to understand and failed to know how to do it. Maybe there were 2 out of 200 students that I saw try to attempt this question that understood how to do it. So let's look at the concept. The concept is about the inverse. So let's get started. So I'm going to start with a question. I always like starting with a question. And you should actually try to answer this. So you want to actually pause and have a think about what you would say as if this was an actual tutorial. The question is, what is the inverse of 2? What is the inverse of 2? So I might write, for example, another way to write that is 2 to the power of minus 1. So maybe you think this is a basic question, maybe you're confused by the question, who knows, but take a second to think about it. So hopefully you've had a go, and this is what I often hear from students. They'll say something like this: the inverse of 2 is 1 on 2. Okay, but let me show you why that doesn't really make sense. It's not really answering the question, because I could have asked you and said, what is 1 on 2? Right? And then maybe you would have said, oh, that's the inverse of 2. Right? Some other answers I've seen are something like 0.5. But think, do you actually know what that is on its own, in and of itself? Do you know what 0.5 is, or 1 on 2, or the inverse of 2 on its own? So you have to escape the shackles of the kind of rote memorization that we learned from high school and kind of trickery that we were put through, which is essentially kind of this mass indoctrination into kind of making you believe you understand something. And in this case, actually, chances are you don't understand what the inverse of 2 is, but don't worry, you will soon. So why is it that these are undefined, right? So firstly, if I'm saying that the inverse of 2 and 1 on 2, what we're writing here, we haven't actually defined anything. Well, what do we really mean by defining something? And is anything really defined then? Well, one way to model things in mathematics is with sets. So most of modern mathematics, not all of it, and there's different models, but one model uses sets at the foundation. Okay, and sets, they're really important. They deserve a whole topic, a whole video, definitely many videos for themselves. But for now, a set is just a collection of objects. Just a collection of objects. And so think about the most basic, it's the most basic possible example of a collection of objects. In fact, it's so simple, it's confusing. So simple, it's confusing. The most basic one, have a think, is the empty set. It's the collection of no things. There's nothing in it. It's the most basic set you could possibly come up with. This is one way that we can actually model the number 0. Okay, there are many different ways to do it, but this is one way. The number 0 is being modeled as the set that has no things in it. It has 0 things in it. That's the way you can think about it. Okay, now let's keep going with this. Let's stretch this. Do you think we can actually define the number 1 really properly, concretely, if we assume that, sets are okay, that sets exist? We can use sets to create new things. Then the question is, can we define the number 1 in a similar way, different, but similar to the number 0? So with sets, and you think, well, okay, if I want to use a set, I mean, it's got to be a set. It's a set with, well, if I put nothing in it, it's the same. We haven't done anything. So I have to put something in it. And the only thing I've got lying around is the empty set. So there you go. This is a legitimate way to model and understand and even define the number 1 concretely, right? And maybe you see the pattern, right? What about the number 2? Can we push this? How far can we push this? Well, yeah, no prizes for guessing here. It's still a set. It's a set, and it's going to have 2 things in it this time, right? 2 things. Those 2 things are going to be, well, one of them we can use the empty set, like we've already used. And the other one is the other thing that we have lying around, which is the set containing the empty set. Let's see. So we can see, yeah, there's 2 things in this set. And we can, of course, there's no stopping this. Nothing will stop us. We can keep going. And as we do keep doing this, we actually end up defining what's called the natural numbers. Okay, the set of all the counting numbers. Sometimes it includes 0, sometimes it doesn't. Here it does. Okay. So the point is now, what am I trying to say is that we can define these numbers 0, 1, 2. We can actually define these. If you're happy with sets, you're happy with these. So now, how can we similarly, concretely define 1 on 2, or the inverse of 2? So you might think a half is kind of like, maybe you're thinking geometrically, maybe you're thinking you take some unit and a half is half the length. That's actually pretty good. But if we're defining things in terms, not kind of in geometry, but more kind of in this more concrete way, you probably can't think of a set with half the number of things in, half something in it. Well, that doesn't make sense, right? So we can't actually define it in the same way. So these are straight up definitions. These are kind of what we might call like concrete definitions, where if we allow sets to exist, we allow existence of sets to be a thing we're happy with, then we can define these numbers. But 1 on 2, the inverse of 2, we can't define in the same concrete way. Okay, so what's the solution? The solution is this concept. So this is the core concept I talked about earlier. This is the core concept that if you don't understand this, you're going to get tripped up time and time again in all the different mathematics subjects at the university level. And this is the concept that all of the students, almost all of the students that I saw at the University of Melbourne, they didn't understand this, but we're going to learn it, right? So the concept is this. The inverse is what the inverse does. So this is, I would say, my most important mathematical motto. Maybe this together with what the inverse does. So I should say what the inverse does. The inverse returns us to the identity. So think about those two mottos. I would say that they are, well, they kind of come together. They're pairs. They're relating somehow to each other. And they are central to all of mathematics and to this question I'm going to show you. So what is this concept really saying? This concept is it's a new way to define a thing. Here again, we've got concrete instantiations, concrete things we can point to, right? Actual sets, and we can say, here are the things. Now we're moving to a definition in terms of a utility. So you might call it like a utilitarian definition, or a definition in terms of its utility. It's a fundamentally new thing that I would say it's not even touched on in high school mathematics. This is one of the many differences. Okay, so it's a definition in terms of utility, meaning what does the thing do, right? Its use. Okay, so think about the inverse of 2. What does the inverse of 2 do? What is its utility? So think about that. Pause the video and hopefully you've thought about it. So it's the number that if I multiply it by 2, I get 1, right? Again, it's the thing that returns us back to the identity. And maybe at this point you're thinking that's really basic. I don't know, maybe it makes sense, but if you don't quite feel the weight of this, consider this, right? Again, 1 is defined over here. We've got a concrete, like we can point to it. It's right here. That's what it is. 2 is defined. It's right here. The inverse of 2 is a new thing that we are defining. It's the thing that makes this equation true. So in fact, instead of writing the thing before we define it, we should say like this. This is much better. 2x equals 1. So let's make this central. We're saying here that the inverse of 2 is the unique number x that makes this equation, that satisfies, let's say, this equation. 2x equals 1. Now, your brain might be auto-completing. Again, this is the indoctrination from high school. Your brain might be auto-completing and saying, oh, that just means that x is equal to 1 on 2. To really understand this concept, you have to get to a point where you should feel like x equals 1 on 2 is basically nonsense. Let me explain why. So if you've done any work with matrices, don't worry if you haven't, but if you have, this will make sense. So what if I wrote this? Tell me what your natural feeling is if I wrote this. 1 over a matrix, 2 by 2 matrix. Does that make sense? Hopefully you're happy that that's just kind of nonsense. Maybe you've never even seen it before and it just looks weird to you. Well, yeah, this should also look weird. In my opinion, it's just my opinion, at least in terms of maths pedagogy, the fact that this thing on the right-hand side here is nonsense, it should imply that the other one is also nonsense. They're both nonsensical in exactly the same way, right? Okay, so forget about this. It really, x equals 1 and 2 is really defined, it's the other way around, right? So it's really going the other way around. It's defined to be the number that makes this equation true. It's the number that takes us back to the identity in relation to 2 and multiplication. That's the key. That's the definition. That's the way to understand the inverse. Okay, so I promised you that this is the concept that you need in order to understand a question that stumped almost every single student I saw in linear algebra at university. And so let me get that question for you, and let's see if we can apply this concept to a real question that students really struggled with. Okay, so here is the question. Let's read it together, but you can pause and read it as well. If A is an n by n matrix, so it's just some square matrix, we don't know how big it is, and it's satisfying, all we know about it is that if we raise it to the third power, so we multiply it with itself 3 times, we get the identity matrix. Okay, then given that, we want to verify this equation. And this equation is an equation involving the inverse of A plus the identity. So you should definitely pause and have a go. And yeah, really, even if you don't know how to start, be in that state and just spend time thinking about it. Even if you feel like, so a common feeling you might feel with this type of question, and this is the feeling that almost all of the students had when trying this, is like your feet are stuck in concrete, like they're glued to the ground. You don't even know what the first step is. You don't know, you can't move. You don't know what to do. So out of that desperation, sometimes I've seen some of these things. So sometimes I'll see something like this. So this is one approach I've seen from many students, and they go like this. So it's good to explore things, even if they're wrong. You have to understand why they're wrong. So I guess spoiler alert, it is wrong. Like, why is it wrong though? Hopefully you're happy with that. But if you're not, just think about numbers. Right, so if I take 2 numbers and I add them up, and then I take the inverse, again, don't forget what the inverse is, right? You can check that this is not true. You can just pick some examples. Just pick, well, almost any 2 numbers will do. Yeah, right? So you just pick some numbers, plug it in, and you'll see, yeah, this is not making sense. It's not true. And a good rule of thumb is that don't forget that numbers are just matrices. They're just 1 by 1 matrices. So if something is not true for numbers, it's also, in general, also not going to be true for matrices, because numbers are just special types of matrices. So this is not true. So you can't do anything there. And so I was like, okay, so if I can't do anything on the left-hand side, like the left-hand side is just, what are you going to do? I've seen people square things. I've seen people square both sides, but either, so imagine if you start with the equation and then you square both sides, is there anything wrong with that? So think about the logic, right? Think about the logic carefully here. It's saying to verify that this left-hand side is equal to the right-hand side, right? That this thing is equal to that thing. Can we use that, and then can we use that to prove that it itself is true? No, right? You can't use the thing you're trying to prove in the proof to prove the thing, right? Otherwise, you're doing circular logic there. So you also can't even take that and square it and mess around with it. That doesn't lead anywhere anyway. So we need to go back to the concept. The concept that I told you is central. The inverse is what the inverse does, right? So the question is asking us to show that the inverse is equal to something. The inverse of another matrix. So let's actually make our lives a little bit easier. And let's call A plus the identity. It's just some other matrix B. Okay, so we're reducing the cognitive load by renaming it. And all they're telling us is that for the matrix B, the inverse is, and they tell us what it is. Well, to verify that it is that. Okay. So the idea is that if someone comes up to you and they give you a matrix and they also say, by the way, here's the inverse of that matrix. The only way to know is to go back to this concept that the inverse is what the inverse does. So in the context that we're within, the context of matrices and matrix multiplication, what does the inverse do? What does the inverse do? For B, it's a matrix, let's call it C, such that, so it's an opportunity to pause and think, what is the equation or the utility or the thing that the inverse does? The answer is this. It's this equation. It's the inverse of B is a matrix, we can call it C, without referencing the inverse of B already. We just say it's another matrix C, such that B times C is equal to the identity. And we actually need to go the other way around. There's a reason for that, and that's because matrix multiplication, you might not know this, that's okay, but one important fact, you can verify yourself that matrix multiplication is not what's called commutative. You can't commute or move one thing past the other in general, because they're not going to be equal, unlike numbers. So we actually need to verify that it's both what's called a left inverse and a right inverse. That's what an inverse is. Okay, so if the point is, one more time, right? The inverse is what the inverse does. So if we can find a matrix C such that when we multiply it with B, we get the identity, then that's it. We've got the inverse. C must be. So from this, it follows that C must be the inverse of B. Okay, so that's what we need to do here. We need to verify that this equation is true for the given matrix or proposed inverse that they gave us. So I'm going to write something. So instead of B, I'll write A plus the identity. I'm going to write something, and I want you to think, is it true? So what I'm going to write is B times the proposed inverse so A plus the identity times this other thing they've given us. And I'm going to write this. Is this true? Or I should say, does it follow from what we've already written, from what we already know to be true? Does it follow? The answer is no. Doesn't follow. That's what we're actually trying to prove. If we can prove that, then we can conclude that we have the inverse. So in general, in mathematics, it's very, very important to have a very clear distinction in your mind between what you know to be true, what is following from what you already know logically, and what you want to prove to be true. Don't mix those up. You have to be very clear in your mind about which is which. So what I'm going to do is just do some matrix algebra. And if at the end I get the identity, we're good. That's what we're trying to prove. So some matrix algebra here. I'll scoot past these details, but yeah, just go back to your matrix algebra properties. So one property is that we can bring the scalar multiple all the way out the front. And now I'm just going to do some algebra here. So I'm just going to multiply through each element. Okay, so pause that and make sure you're happy with that. Now, looking at this, we can see there's some cancellation, which is nice. That's always a good sign. And now we have 1/2. Well, that's nice because that's coming back to what we said earlier, but we'll get to that in a second. So we end up getting 1/2 times a cubed plus the identity. Okay, well, what do we do now? Well, let's not forget, there was only one property that we knew about, that we were given about a, which is that its cube is the identity. Well, perfect. So we have, instead of writing 1 on 2, I just said that was nonsense. So I'm going to write instead the inverse of 2, because that's what that is. It's the better way to think about it. And a cubed is the identity, so there's one identity plus another one. So we have 2. And beautiful, the concept of inverses is coming again, because we get 2 times the identity times the inverse of 2. Beautiful. 2, the inverse of 2 times 2 is just 1. That's the whole point. Firstly, we can collect the scalars out the front here. We get the whole definition of the inverse of 2. And finally, we get the identity. Okay, so once again, just pause this. You should pause it now and think, what have we just seen? What have we just witnessed? What have we just verified or proven? So to see, we've taken a matrix. We called it B at some point, but it's just some matrix. We multiplied it by some other matrix, right? And what did we get? We got the identity. So we can say that this matrix, this term, this expression, that is just a matrix, is doing what the inverse ought to do, and therefore it is the inverse. So this is at this point. Now you have to do it both ways, so you have to multiply it the other way, but you can do that on your own. So at this point, once you've done that, you can conclude that this expression here is just doing what the inverse does, and therefore it is the inverse. Okay, so let's recap to finish up. So we said, I said that, okay, so start all the way up here. We said that we can define numbers properly, concretely, like 0, 1, 2, in terms of sets. Sets are our kind of foundation, at least in one interpretation of how to actually define things properly in mathematics. And 0 is defined as the set that has nothing in it, and 1 is like this, and so on. And so we're happy with it. 0, 1, and 2, and 3, and 4, and all the other natural numbers, we're kind of happy with their existence. We know what they are. They're concrete. We can write them out like this. But we can't do the same for 1/2. In fact, it's an interesting thing, because it's a new thing. Again, we can't define it concretely in the same way, same exact way as the others. So instead we have to define it, or we do define it, in terms of its utility. So this is the first level of abstraction in math. Well, there's many levels of abstraction, but we can see a different level of abstraction when we go from concretely defined things to things defined with respect to those original things, but in terms of a utility. So how they behave in relation to these things that already exist, right? And that can be summarized succinctly with this motto, which I think is the most important, one of the most important mottos in higher mathematics. The inverse is what the inverse does. And the inverse is, what does it do? It takes us back to the identity. Okay, so they said to verify that for some matrix, the inverse is something. So to verify that this is the inverse, we need to check that it does what the inverse ought to do, which is that if we multiply it with the matrix it's meant to be the inverse of, we should get the identity, and we did. So therefore it is the inverse. So I hope you can see why the concept is a prerequisite to answering this question. And I've seen that firsthand with hundreds of students, and it doesn't just come up in this single question. This concept is very, very deep. So anytime you see inverses of functions, inverses of numbers, inverses of matrices, inverses of group elements, of ring elements, it is everywhere in mathematics, and most of mathematics is really just about when does an inverse for a particular thing exist and when does it not? It's a very deep concept. Okay, so let's leave it there. I hope you enjoyed that and see you in another one.